In this lesson, we're examining scatter plots and correlation, so let's get started. A scatter plot is a graph of plotted points that show the relationship between two sets of data. This is called bivariate data, that is data for two variables, usually two types of related data. And here we have an example of a scatter plot. As you can see, the dots are spread about. And we have three types of association with scatter plots. We have a positive association, and think about how we read. We read from left to right. This graph goes up from left to right, so that is why this is a positive association. Of course, the negative association would be going down from left to right. And then we also have just a scatter association, or no association at all. And so we have these three types of scatter plots here. Now we're looking at identifying the function model that best fits the scatter plot. The first graph we have here is similar to a line. It's going in one direction, and so that would be a linear model. That line, we could actually just kind of draw a line that is in the shape or in the same direction as the dots. This is called a regression line, and this is a linear model that fits the data, and it's also called the line of best fit. And this is used to make predictions based on a relationship modeled by the data. Next, we have this U-shaped set of points, and if you think about a U-shaped graph, what comes to mind? Hopefully you were thinking parabola shape, and so this would be a quadratic model of a scatter plot. And next, this kind of scoops up, right? It goes up exponentially, so kind of gave you a clue there. This is an exponential curve, and so this is an exponential model here. And next, this is just scattered about, and so we don't have any association here. Let's take a look at example 1 here. It says the monarch butterfly is essential to the pollination process of many native and farm North American plants. These butterflies migrate thousands of miles over several months. A Florida Department of Forestry outpost in Hawthorne, Florida, has been tracking their population since the 2005 migration cycle. I'm just going to underline 2005 because that is the starting point when they started to track this data here. So let's look at part A. It says represent the data on this scatter plot, labeling your axes. And so we have the larger numbers for our y value, y axis here. And so that would be my population in millions, because our population is in millions on our chart here. And then at the bottom, that would be the years since 2005 there. All right. So let's go ahead and plot these ordered pairs. So this would be like our x, or our horizontal, and then our y here. So independent and dependent variable here. All right. X and y, independent and dependent. So I'm just going to plot these ordered pairs. 0, 296. 0, 296 is about here. 1, 334. And it's not going to be exact. So 1, 334, I'm going to say it's about here. Next, 2, 231. 2, 231 is about here. 496. 96 is about here. 5, 201. About here. Next, 6, 145. Let's see, about here. 760. And then about here. And 833. A little above the 25. Alright, so I've made my scatter plot here. Alright, part B. It says, what type of model do you think best fits the data? Justify your answer. And this would be linear, because points follow a linear pattern. Goes down. from left to right, so kind of it's a linear pattern. And then next, part C, of the following choices, which equation is the best fit for the data? So we have our choices here. Since this graph falls from left to right, we can automatically eliminate A and C because that is a positive slope. So remember, slope-intercept is y equals mx plus b. So m is our slope, and so it would have to be a negative slope. So it would be between b and d. And if you look at your y-intercept here, right here, y-intercept is 0 to 96. So that is positive. So a model, so we know we don't have a 296 here, but it says the best fit. And so since it's positive, I'm going to go with this positive 320 because we have a negative. And so the best fit would be D. So now we're analyzing this graph and this information a little bit more. For parts D, E, and F, I have the graph here that I plotted, and I have the line of best fit right here because we're going to use that to answer these questions. So part D, it says, what is the predicted population size for the year 2010? How does that compare to the real data, round to the nearest million? So if you recall, they started their research in 2005. All right, so 2010 would be 5 years later. And we're going to use the line of best fit to predict the population. So that's f of x is equal to negative 34, and I'm going to plug in 5 for x. That's my years, my independent variable. All right, 34 times 5, or negative 34 times 5 is negative 170. And minus, that should be 320. Plus 320, that is 150. And so it is in millions, and so it would be around 150 million for that prediction there. All right. Next, part E, in what year is the population predicted to go extinct? I'm going to say, so this graph is over a 10-year period, and so if you look at this graph here, at 10 years, there's nothing there. So I'm going to say about 10 years, but we can plug it in to make sure to the line of best fit. If we plug in negative 34 times 10, so I'm plugging in 10 for years, just to see. So of course that would be negative 340 plus 320. So we're going to get a negative number, so I'm going to say after about 10 years, because if you plug in 10, you're going to end up with a negative number, so can't have a negative population there, so about 10 years. And then last, part F, it says demographer Carla Wilson determined that by her calculations, the population that traveled through Hawthorne would be at 8 million mark in 2018. Do you agree or disagree with her hypothesis? Justify your answer. In 2018, that's 13 years later, right? Because if it started in 2005, that's 13 years later. So we've already determined from part E that after about 10 years, the population would be extinct because we would be at 0, well, less than 0. So according to the line of best fit, the population would be at 0 after 13 years there. Now let's take a look at correlation coefficient. A correlation coefficient is one measure of strength and direction of a linear association, and it is expressed using the variable r. So if r is positive, that indicates a positive correlation. If the value of r is negative, that indicates a negative correlation. Also, the value of r ranges from -1 to +1. So the lowest would be at -1, the highest would be at +1. The stronger the correlation, the closer r is to 1 and -1. So strong correlation, your r value is close to 1 or -1. And then for a weaker correlation, your r will be closer to 0. And so here we have a graph here. So the first one we're going to look at, you have a strong negative. The correlations lie on the line, but it has a negative slope, and R is close to 1. So we can see how they're tightly packed together around this line here, that they're close together. Next, for the second one, we have a positive strong correlation because once again, you see these tightly packed dots. They're close together. So again, your R would be close to positive 1. So strong negative, R is close to negative 1. Strong positive, R is close to positive 1. Now let's look at a weak negative. So we see how for this third graph here is kind of spread out, or the dots are spread out. You have a negative slope, which is why it's negative. The graph falls from left to right. And your R would be between 0 and negative 1 because it is negative. And it's not going to be as close to the negative 1 because it is weak. So remember, it's weaker. It's going to be closer to the 0. For the weak positive, it's positive because that graph goes up from left to right, but it's loosely packed. And your R will be between 0 and 1. But of course, it'll be closer to 0 because it is, sorry, it'll be close to 0 because it is weak. Let's take a look at example 2 here. It says, using the values in the boxes, indicate which of the following values of R best describe each of the scatter plots. And so let's recall a few things. Remember, if it's a stronger correlation, the value of R would be close to 1 or negative 1. If it's a weaker correlation, the value of R will be close to 0. So as an example, if we have R is positive 0.45 and negative 4.5, they have an equal strength, but they go in opposite directions. This would be a positive slope, and this would be a negative slope. So now let's match the values of R, or correlation coefficients, with the graphs down here. So the first thing I like to look at, if I have to do a matching activity for this type of problem, I want to look for the stronger correlations, and so that would be the first and last one here. So the first one, it has a negative slope. It falls from left to right. So I want to look for a negative number that is close to negative 1, and that would be negative 0.0991. It's close to negative 1, and it's so that's the strongest one there. So I'm going to mark that out. Next, this is strong as well, but it is positive. So I'm going to look for a R value that is positive and close to negative and close to positive 1, and that would be positive 0.990. I'm going to cross that out. And next, let's look at, so the only one I have left, I have these three graphs in the middle. So I have a positive graph here, right? And the other two graphs are negative. So my only positive R value left would be 0.0790. And of course it's going to be stronger, so it's closer to 1. And if you notice, the other two that are remaining, they're closer to 0. So I'm on the right track here. So this is positive, and this is closer to negative 1. So next, I can look at this one. This is the weakest because it's completely spread out. And so this would be closer to 0. So, and it is negative because it falls. And the only one that is left here is, of course, the negative 0.05. So it falls again. It's weak, but it's not as weak as the third graph right here. And so I have matched the scatter plots with their corresponding correlation coefficients. I would like for you to try this example on your own. It says, when looking at attendance data for the year 2020 and 2021, a principal graphed the number of tardies, X, a student had when compared to their grade point average, Y. The principal found the correlation coefficient to be R is equal to negative 0.94. So go ahead and pause the video and try part A and B of this example here. Hopefully you got the answers correct. There's a strong relationship between the tardies and the GPA. That is because our R value is close to -1. It is linear because our tardies are represented by X. And the slope of the graph is negative because our R value here is negative. The sketch of the graph would be a line that falls from left to right. Our X values are tardy, so right here. Our Y is the GPA. So as you can see here, as an example, if I just pick this point here, let's say that this point is 10, 1, just estimating here. If a student has 10 tardies, the GPA would be at 1. So I just made that up, but you can see the relationship. The more tardies that the student has, the GPA is lower. The last thing I want to show you in this lesson is correlation versus causation. And a common error when interpreting a paired data is confusing correlation and causation. So let's see the difference. A correlation describes the degree to which two variables move in coordination with one another. Causation is a relationship between two events where one event is affected by the other one. So if a correlation exists between two variables, this does not necessarily mean that one variable causes the other one. When one variable increases, the other variable may increase or decrease as a result of other variables that are not considered. Such variables are sometimes called lurking variables, and so sometimes there is a correlation within a relationship, but one doesn't cause the other one to happen. So let's look at some examples, and so you can see how we can relate this to some real life situations here. Example 4, we want to select cases where there is a causal relationship. So the first one here says there is a strong positive correlation between the number of touchdowns per football game and the final score of the football game. Yes, the whole point of football is to score the touchdown, so that will of course affect the final score, so that would be a causal relationship. The next one, the number of umbrellas sold is positively correlated to precipitation levels. No, just because more umbrellas are sold doesn't necessarily mean it's going to rain. Umbrellas sold is not going to make it rain. All right, so number 3, the number of stops at a school bus makes in the morning route is negatively correlated with how many students ride a particular bus. No, stops do not relate to how many students ride the bus, so no relationship there. Next, there's a strong negative correlation between the age and number of toys purchased for one's birthday. You cannot predict that. You just can't predict how many presents someone is going to get. Next, there is a moderate positive correlation between the amount of rice a family eats per month and the amount of oranges sold per month in the south of US. These two items do not relate at all. And the last one, there's a strong positive correlation between the number of cigarettes consumed and the number of cases of lung cancer diagnosis. That would be a causal relationship. The more people smoke, the more people would get lung cancer. So only the first one here and the last one here are causal relationships. Alright, so we've reached the last problem here, and I would like for you to try this one on your own. Go ahead and pause the video and try this problem on your own, answering parts A, B, and C. Here are the answers here. Hopefully you got them correct. You may need to pause the video to check your answers, and it may need to be paused a little longer if you did not get them correct, but hopefully you got them correct here. We've reached the end of our lesson. I want to thank you for learning with me. Some related videos are two-way frequency tables and describing data using shape, center, and spread. If you haven't already, please like, comment, share, and subscribe. And once again, I want to thank you for learning with me.